So here's a simple task. I want this. I want it to sound teeny. Like, this is a modern recording. This is something we recorded 2010. To sound more like this. Instead of now, being a modern guy, I want it to sound old-timey using modern tools. So what I would do is go to something like Pro Tools or Adobe Audition or one of these products and go ahead and pick the tinny tool. Only there isn't a tinny tool. If you think about it, there isn't even a loud tool. It's called volume, or a warm tool, or a muddy tool, or a sharp tool, or a bright tool, or any of the adjectives people often use in English to describe sound. Instead, we have panners and normalizers, flangers, phasers. So there's a problem here that there's a mapping issue, tools to concepts. And then if I do have someone tell me that a parametric equalizer will make something tinny, I have the problem of understanding how to use a parametric equalizer. Here's a typical parametric equalizer. It has 40 controls, 32 knobs, and a bunch of buttons, and there's no tinny controller. So the basic paradigm we want to flip is, instead of you're spending 6 months learning equalization tools and reverberation tools and flanging tools, etc., why not have the tool spend 6 minutes or 60 seconds or 6 seconds and learn what you mean by the word tinny? And the straightforward way this works, if you work with something like a recording engineer, is if you come to them and you say, I've got a word you've never heard before, I want the stuff to sound splanky, is the recording engineer looks at you in puzzlement and then says, could you describe that in some other words? And when that fails, he starts manipulating things and asking you, does this make it splankier? So that's what our basic interaction paradigm is for a learner. You take the original sound and have a listen. And here I'm using an equalizer. Then it tries some EQ settings. And every time you hear one, you rate it from +1, that's really tinny, to -1, that's the opposite of tinny. And as it gets ratings from you, it figures out which frequency bands are correlating with your impression of what makes something tinny. And what you end up with is some kind of a tinny controller. This is now actually a commercially released audio plugin, and actually not just an audio plugin for EQ. We went ahead and did it for reverb, and then people did it for color correction for Photoshop, and then people did it for hearing aids as well. Hearing aids are a great example. If you were thinking to yourself, but I really enjoy working with parametric equalizers, why would you give me a new interface? I'm here to tell you that the people who have hearing aids generally don't want to have to learn to control 30 knobs in order to improve the sound of their hearing aid. They just want it to sound better now. I said that it requires up to 30 examples to learn. And that's way better than you're spending 6 months learning Pro Tools, but it's not as good as it could be. Some people don't want to go to this much work. So we'd like to be able to reduce this by a factor of 10. How can we make audio manipulation or image color or hearing aid manipulation tools that can learn from you really quickly what it is you want without your having to work the detailed controls, talking about, bandpass filters and whatever. That recording engineer, if you use a word he's heard before, something like tinny, he doesn't start at a place of complete ignorance. He starts from some knowledge of what other people in the past have said when you say tinny or bright or warm. And so they can home in on something much faster than with 30 examples. So these are actually 3 different equalization curves taught to our system by 2 different people. And one thing I just want to point out is, although each of us has our own unique idea of what makes a sound tinny or bright, our concepts are often related, even if not identical. but that relationship isn't always as clear as you might expect. For example, these three here, I would argue that user 1's tinny looks more like user 2's bright than user 1's bright does. So these two may share a concept, but user 1 doesn't like that concept so much and calls it tinny when you boosted up the 4,000 hertz band, and user 2 gives it a more neutral kind of term, bright. So when we're transfer learning, when we're using knowledge from past people, we can't simply count on grabbing someone else's pre-made bright in order to use it for you. It might not be exactly what you were after. Well, let's say we have a set of user concepts, and a user concept is a concept taught to the machine by a particular user. We could have some original audio that got manipulated in different ways, and each of these users went ahead and rated how well they liked that manipulation in light of the concept they were trying to get across. And when we do that, this gives us something like a collaborative filtering rating space, okay? So I can take, say, the Sue's ratings of examples 2 and example 3, and this gives me a two-dimensional coordinate system to put Sue's warm into a rating space. And if I do that for these three concepts, now I've got fat, warm, and dark put in a rating space. And what good is that? Well, if I'm doing something akin to collaborative filtering, then when a new concept comes along, instead of starting from scratch, what we're going to do is we're going to ask a smaller number of questions to place you in a space of past concepts, and then we're going to learn without having to necessarily ask you for 30 rated examples. And the way we're going to get around asking for so much data from you is we're going to reuse training data from other people. And that training data is going to be weighted based on the distance of their concept to your concept in the rating space. Okay, so in this example, fat would be more influential than warm would be, even if the word that I'm teaching at this time is warm. We call this pooled transfer learning, where we're using all the words, all prior data has influence. We also took a look at same word transfer learning, where it's just like it sounds. You only use the data from prior concepts that share the exact same label. Instead of asking for 30 rated examples, ask for a much smaller number, say 3. Use those ratings to locate the new concept in this concept space. And then train the system using responses that people gave when teaching other concepts to it. And we're going to weight the influence those other concepts have based on the distance to your concept. That's it. Pick the middle one because it caused the greatest variation in what people's responses were. So this is an actual rating space, and what this is what's 172 divided by 2? 86? This is 86 user concepts placed in the space of the two most controversial examples presented to the users when we were training the system. And there were 5 words that we did on this paper: bright, tinny, warm, muffled, and broad. And so this is just a 2D representation here, just most controversial and second most controversial question. And actually what's kind of cool about this is, just from this, I could train a classifier to separate bright from muffled pretty well. I could just draw a diagonal line from the lower left to the upper right. I could separate tinny from warm and broad pretty easily with a different diagonal line. Tinny's in the upper right, warm and broad in the lower left. Obviously, warm and broad appear to be concepts that are overlapping heavily in this space, so you might need more questions, or they might be overlapped concepts. Different labels, coming back to this idea of exclusive labels for things. There might not be an exclusive label for this concept. Some people may call something warm that another person calls broad. So we went ahead and trained up a system that compared how well it could predict what your answer to the next question would be based on different kinds of learning. So what I mean by that is the system is presenting you examples. And what it does is, after every example it presents to you, it makes a new model of your concept. And based on that model, it tries to predict what rating you would give the next example it's going to provide you. And the higher the correlation between the rating that it predicts you would give and the rating you actually give, we say that the machine has learned something. Okay? And so the game here is, if you look at the bottom sort of dashed line, that's our baseline learner. It starts from knowing nothing and takes a guess as how you're going to rate the next example. Then after one example, 2 examples, 3 examples, it gets better and better at guessing what you would call, how well you would rate the next example it presents you. The next line up from that is the dashed green line, and that's the pooled transfer learning. That's where it uses all the information it's got from all the other words that it's learned so far. But it doesn't do this step here of picking the most controversial question first and then going to the second most and the third most. It randomly picks. So you get some improvement by just randomly picking stuff and seeing what you would answer. You get more improvement, significantly more, by allowing for this controversy thing. Pick the most controversial questions first to narrow down where you are in the space. And you can see that by doing that, after rating 3 examples, I can do about as well as rating maybe 20 or 30 examples with the baseline learner. Be nice, they're going to tell you it's good. So it's nice to put in a random control to tell you how good you're doing compared to just doing something random. But the good news is our controllers are actually doing significantly better than random. It's not chance, that difference. The bad news is that people are a little nicer to us than we deserve. This is what I've just described as sort of a new paradigm for media production tools. Instead of you're having to learn all these controllers, you're just rating examples and giving it sort of creative feedback